Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into the very last section of Chapter 1, which is Section 1.11. In this section, we're going to investigate some special higher-order differential equations, basically some very special second-order differential equations that we can solve based on our investigation of first-order differential equations. Now, this is sort of a unique little section to sort of end Chapter 1 on, because in some ways, what we're going to see here is that the techniques we've developed for first-order differential equations, while we do have a lot of sort of interesting techniques that can handle lots of different situations for first-order differential equations, they really don't help us with higher-order differential equations unless we're in some very special circumstances. And we're going to break these into three major cases, what we call Case 0, Case 1, and Case 2. The reason that sounds a little bit weird to start with Case 0 is because in your textbook, they only discuss Case 1 and Case 2. Case 0, I think, is worth mentioning, so we're going to sort of include that as well and have a brief discussion of that. But in some ways, the sort of point of this section is to show you that higher order differential equations with what we currently have are very challenging to sort of solve. So that'll sort of motivate us for our move into Chapter 2 and beyond, where we'll switch gears for a while and start talking about linear algebra. And we'll spend some time discussing and investigating linear algebra. And then once we have some mechanisms from linear algebra, we'll be able to return to higher order differential equations and solve them a lot more easily than we would be able to right now. So, for now, we're just going to take a look at some very special cases of second-order differential equations that we can solve using what we've investigated so far for first-order ones. So, this is some second-order differential equations. So, the first case that we're going to talk about is what I would call the missing y and y prime case. In other words, this is going to be a second-order differential equation, so it's going to have a y double prime in it, but it's going to be missing both the y and y prime in the actual differential equation. So, as a sort of motivating example of this, imagine this situation here. Y double prime minus 6x cubed equals sine x. So you'll notice that this is a second order differential equation, but there are no instances of the dependent variable or the first derivative here. So, this is a motivating example because we actually could probably just sort of logically figure out how to solve this. Let's imagine sort of isolating this y double prime, and also just in general to help us sort of see this, let's also rewrite the y double prime in a more sort of expanded differential notation. So I'm going to rewrite this as the second derivative, more like this, just so we sort of remind ourselves this is the second derivative of y with respect to x. And we're going to rewrite that as sine x plus 6x cubed. So it makes sense to sort of put this over here. You know, generally it's good to see the differential equation as being equal to this. Why we're expanding it here? Well, there's not really any main reason except that it just helps us remind ourselves we're treating y as the dependent variable, x is the independent. All good. Well, if we think about this, though, we can sort of rewrite this as the first derivative with respect to x of the first derivative, right? I mean, that's what a second derivative is. It's the derivative of the derivative. Equals sine x plus 6x cubed. And now what we can do is we can integrate with respect to x on both sides. So we're going to integrate with respect to x on both sides. So we're going to get the integral of the derivative with respect to x of the derivative of y with respect to x dx is going to be the integral sine x plus 6x cubed dx. So we're going to integrate with respect to x on both sides. Now on this side, it should be very easy. The integral of the derivative is just going to be whatever was there, so the dy dx. That's an application of the fundamental theorem. In some ways, we're saying if you take the antiderivative of the second derivative, you should get back to the first derivative. On the right-hand side, we can go ahead and immediately do that. Integral of sine is negative cosine. And of course, the integral of that 6x cubed, well, if we do that, we're going to get a x to the fourth, and looks like we're going to get like a 3 halves x to the fourth there. Then, of course, we've done an integral, so we should include an unknown constant, c there. Okay, but now what do we notice about this? Well, this is a first-order differential equation, and we can go ahead and solve this as well. I guess we could view this as a separable differential equation, right? The x is over here, and there is no y, so we could just think about it as a y. So we can note that this is now what we call separable. So we could integrate 1 dy, we could integrate negative cosine x plus 3 halves x to the fourth plus c. Got to integrate that constant as well, dx. Then, of course, on this side, the integral of 1 dy is y. Over here, we could integrate that. Integral of cosine is sine, so we get negative sine x. Plus, this is going to go up to x to the fifth, so we get 3/10 x to the fifth. Plus, the integral of a constant is that constant times our variable. And, of course, we've done another integral, so we have to include another constant integration, plus d. And there we go. There's our solution, right? Y equals negative sine x plus 3/10 x to the fifth plus cx plus d for our actual second order differential equation. So we actually managed to solve a higher order differential equation. Now, I do want to just mention one sort of interesting thing. Right here at this step, we said it was separable, and we sort of proceeded here. Notice that since there is no function of y, we could have also just integrated both sides with respect to x again, used fundamental theorems to say the integral with respect to x of dy dx is going to be y, and then just integrate this side with respect to x and get the same result. The only reason I mentioned separable here is because that's a technique we used for first order, so I just wanted to reference something we did for first orders. But actually, this is even easier than a separable differential equation because we could again just integrate with respect to x. So this tells us sort of a general approach for how to deal with this case 0. If you're missing your y and your y prime, what you can do is you can simply isolate that second derivative and then integrate with respect to x twice. So let's summarize that and take a look at one more quick example and then move on to the more interesting cases. So the main idea for case 0 is you should isolate the y double prime and then just simply integrate twice. And since you're going to integrate twice, remember, you're going to have two unknown constants of integration. So not much to really say about case 0. It is going to be the simplest of the three cases we're going to talk about, but there we go. Let's go ahead and try to solve then all solutions to this second order differential equation. Y prime, y double prime equals y prime e to the 2x. Now we might look at this and say, hey, that's not actually a case 0 because it's got that y prime. And we said case 0 is supposed to be missing both the y and the y prime. And this guy clearly is not. So maybe this is a new case. Well, maybe it is a new case, but actually we should be able to still use our old approach by just simply dividing both sides by y prime. So let's divide both sides by y prime and get y double prime is equal to e to the 2x. Now, of course, we got to be a little bit careful. We divided by something that involves a dependent variable. So that makes the assumption that y prime is not equal to 0. So we'll deal with that in a moment. From here, though, this certainly is case 0. It's just y double prime, and it's already in that nice format. So we can say y prime is going to be the integral e to the 2x dx. I'm skipping writing everything out now since we sort of know how this is going to run. We're just going to integrate twice. That should be pretty easy. That's y prime is 1/2 e to the 2x plus some unknown constant. We integrate again, integral 1/2 e to the 2x plus c dx. And looks like we get 1/4 e to the 2x plus cx plus d. So there we go. There's our solutions. Now we got to go pay attention to this. Y prime not equal to 0. Let's go ahead and check this over here. Y prime equal to 0. Well, what types of things have a derivative equal to 0? Well, that actually means that we might have solutions that are just constants, right? Y prime being equal to 0. That's like a little mini first order differential equation. The solutions there are constants. Are constants really solutions here? Well, you plug them into the left-hand side. The derivative of a constant is 0, so it'll be 0 on the left-hand side. And there's a derivative on the right-hand side, so that'll be 0. So these do work. So we would also have all the constant functions as solutions. Are those actually included in here? Well, we could certainly choose c equals 0 and get rid of that linear component. But notice we're always going to have that 1/4 e to the 2x in here. So, unfortunately, there's no way to write these constant solutions in this format, so we're going to have to include these as well. So our solution set is going to be y equals 1/4 e to the 2x plus cx plus d, along with everything of the form y equals c. If you don't like reusing the same constant, let's use just a new constant. Let's say y equals k. So that's our solution set to this second order differential equation. There's no general solution this time because not everything can be written in one format. You've got things that look like this and you've got things that look like that. All right, so that's pretty much all I want to say about case 0. Now let's take a look at case 1, which is a little bit different. For case 1, we're actually going to analyze case 1 before we take a look at an example. So case 1 is what we reference as the missing dependent variable, meaning that there is no y in your differential equation. So if there is no y in the differential equation, then you should be able to rewrite the differential equation as the second derivative is equal to a function of x and the first derivative. Why do I know we can do that? Well, because there are going to be no y's in the differential equation. So if you isolate the second derivative on one side, everything else that remains is just going to be in terms of x, the independent variable, and the derivative. All right, then we're going to try to apply this substitution. V equals dy over dx. So we're going to use v equals dy dx. Then we can think about the second derivative. So the second derivative of y with respect to x as the derivative with respect to x of the first derivative. That makes sense. That's how we normally think of the second derivative. But since v is equal to dy dx, we can put v in there. So we're taking the first derivative with respect to x of v, and we can just call that dv dx. So in other words, if we sort of grab from here, we're basically saying that dy dx is going to be equal to v, and the second derivative with respect to of y with respect to x is going to be viewed as dv dx. So if we pop those in, then the left-hand side can just be viewed as dv dx. That's what we have here. And this f of x dy dx, well, is now going to be a function of x. And of course, the dy dx is equal to v. So we have this equation now, dv dx is equal to f of xv. What's so fancy about this? Well, we don't know what the equation is, but we do know one thing. This is now first order. This is first order with v as the dependent variable and x still as our independent. So is that meaning that this is going to be easy to solve? No, not necessarily, but it is a first order differential equation, which is what we've learned how to solve. So in other words, we've reduced from a second order differential equation to a first order one, and then hopefully we can solve that. So you can then sort of say that you finish up this technique. You can say that you finish up this technique here. Sorry, let me just there we go. Zoom out there. You can finish up this technique by then working through and solving this first order differential equation using any technique that you like. And then you can undo the substitution, v equals dy dx. And since that'll be one more first order differential equation, because it'll basically tell you about the first derivative of y with respect to x is equal to some function, you solve one more first order differential equation and you're good to go. It's not a coincidence that in other words, in this case of solving this second order differential equation, we're going to have to solve two first order differential equations. First this one, and then one to undo the substitution. So let's go ahead and take a look at an example of this. So for our example, let's go ahead and take a look at this guy here. So we want to find all solutions to this second order differential equation. This is certainly a missing dependent variable, so we can just make our note here. This is missing dependent, so it's missing that dependent variable y. So it is indeed going to be this case 1 that we just talked about. So our idea here is we're going to let v be equal to y prime, and that means that that dv dx is going to be equal to that y double prime. That's going to be our substitution. And, you know, notice that I'm sort of mixing those notations. I mean, the y prime and the y double prime are great for shorthanding things, but as you guys can sort of see, because we're changing variables, it might be nice to sort of use this notation to remind ourselves, okay, we still have x as our independent, but now we're going to be thinking about v as dependent. So let's go ahead and do that. So this right here then, that y double prime is going to become dv dx minus this y prime, which we can think about as v, and then we have our e to the 2x. Now, what type of differential equation is this? Well, it's certainly first order, but it's even better than that. This is linear, and it is in standard form. So that's great. So we can go ahead and immediately go to our integrating factor, e to the integral of -1 dx which looks like we're going to be getting e to the negative x as our integrating factor. So let's multiply everything by e to the negative x. E to the negative x dv dx minus e to the negative x v. And we multiply e to the negative x with e to the 2x. We get e to the x. Okay. Left-hand side, it's linear, so this has got to be a product rule now. So it should be e to the minus x v, and then prime. Of course, that is the derivative with respect to x. And that equals e to the x. You know what? Just to stay more consistent here, I don't want to have to keep having you guys go back and forth. Let's just put our dd dx there to remind, since that's the derivative notation we're sort of using. Again, doesn't matter. Okay, now we can integrate both sides with respect to x. So we get e to the negative xv is the integral of e to the x dx, which means we get e to the negative xv. When we integrate here, looks like we should get e to the x plus c. All right, now we can go ahead and solve for v. So let's multiply by e to the x, and we get v equals e to the 2x plus c e to the x. All right, so we've managed to solve for v. Now we can undo the substitution. So the substitution was v equals y prime, or better maybe to think about it as v equals dy dx. So let's go ahead and pop that back in there. We get dy dx is e to the 2x plus c e to the x. Now we're back to our dependent variable that we originally wanted, y. Notice from here we can just integrate directly. So we get y is the integral e to the 2x plus c e to the x dx. So that means y is 1/2 e to the 2x plus c e to the x. And then since we integrated again, another constant of integration. Since these are all second order, we're expecting 2 constants of integration each time. And there we go. There's our general solution here to this second order differential equation. So this is an example of a missing dependent. Missing dependent is maybe slightly harder than case 0, but it is still very easy. It's just a direct substitution, letting your new variable stand in for the derivative. The derivative of your new variable is then the second derivative. You can plug everything in. You should get some sort of first order. Not guaranteed to be linear, but it is guaranteed to be first order. Solve it however you can find a way to solve that first order. We went through all that, got down to here, solved for v, undid the substitution. Unfortunately, it's not just an algebraic substitution, so after we undid the substitution, we still had to integrate one more time, and that gave us our general solution. All right, let's look at one final case for a second-order differential equation. This one's a bit more complicated. It's called case 2, and the reason it's a bit more complicated, just to sort of mention before we get into the details of it, is because we're going to be changing at some moment the independent variable. So case 2 is where we have a missing independent variable. So in other words, this means we have a second order differential equation where you see y double prime, you see y prime, you see y, but you see no x's or functions of x's anywhere in the differential equation. So if you have something that is a case 2, then you can write your second order differential equation as the second derivative is equal to a function of the dependent variable and the derivative, because of course you don't need any x's because, well, there are no x's in the actual equation there. So we're going to apply the same substitution we just mentioned, v equals dy dx. So we're not going to change the substitution, but we're going to change how we think about the substitution for the second derivative. And the reason we're going to do that is because we want to avoid using x as the independent variable. Back here in case 1, there were x's in the equation, so we might as well keep the same dependent variable. So when we went to do v and ultimately looked at the second derivative, we were okay with thinking about it as dv dx, where x was still treated as the independent. That's not going to help us in case 2 because we'd like to get rid of x as the independent variable and actually change to y as the new independent variable. So our trick is going to be to still use the same substitution, v equals dy dx. But when we go to consider the second derivative, we're going to think about the second derivative as the derivative with respect to x of the first derivative. We're going to think about the first derivative as equal to v, same as before. But then when we go to apply the first derivative with respect to x of v, this is sort of the key moment here. When we do this here, we're going to apply chain rule. And we're going to think about v as a function of y as a function of x. So when we apply this derivative with respect to x of v, we're going to think about v as a function of y as a function of x. So we're going to get dv dy, dy dx. And then we're going to be really clever, and we're going to say that that dy dx right there, that's equivalent to v. So we can say that that dv dy, dy dx is actually dv dy v. So when you guys use this substitution here, what you're actually going to use is you're going to say that the second derivative of y with respect to x is actually equivalent to dv dy v. That's actually what we're going to grab from all that work there. Now that might not look like much, but the whole key here is we're going to think about the second derivative as the first derivative of v with respect to y. In other words, y will now be our new independent variable, and v will be our new dependent variable. So this starts off with the same substitution, but it ends with a very different idea there. Now that we can do that, well, we can think about the left-hand side as dv dy v, and the right-hand side, which had y and dy dx, as y and v. And now, of course, that is first order again. So once again, we've reduced the order from second order to first order. So then you can solve this as a first order with whatever technique you like, and then undo the substitution v equals dy dx, just like before. So the big key here is that you're still going to use the same first part for the substitution, but you're going to be using this as sort of a follow-up when you try to go and remove the second derivative. Remember, it's going to be dv dy times v. So let's go ahead and take a look at an example. Well, here's our differential equation. Notice it is certainly second order, and it is certainly this case 2, missing independent variable. Okay, so let's go ahead and do our substitution. We're going to let v be equal to dy dx, and then we're going to let the second derivative with respect to x be actually equal to v dv dy, right? That's what we sort of derived right here. That's the sort of piece you want to remember from this technique. So we've got the second derivative is equal to dv dy times v. So let's pop that in here. That's the second derivative, so we can plug that in. So we get v times dv dy plus 2y to the minus 1. Then that y prime squared can now be thought about as v squared. So we get v squared is equal to y prime, which of course again we can think about as v. So now we have a differential equation that is first order where y is independent and v is dependent. So first thing we could maybe notice here is that there's v's in each term. So let's divide by v and get dv dy plus 2y to the minus 1. V is equal to 1. Of course, we'll have to be a little bit careful. We'll have to go back and consider that that's when v is not equal to 0. All right. What do we notice about this? Well, it might look a little bit weird. We might say, well, I don't like that y to the minus 1. But remember, y is independent now. So this is actually linear and in standard form. So this is linear plus standard form. To see that a little bit better, you can rewrite that as dv dy plus 2 over y v is equal to 1. And again, that 2 over y is all good because y is being treated as the independent. So the integrating factor, e to the integral 2 over y dy, is going to be e to the 2 ln y, which, standard trick, put the 2 up as an exponent, ln of y squared, cancel it out, we get a y squared integrating factor. So let's multiply through, we get y squared dv dy plus 2yv is equal to y squared. Now this left-hand side should be a product rule. So y squared v, and this would all be d dy equals y squared. You can check that, differentiate the y squared, that's going to give you the 2yv, differentiate the v, going to give you that y squared dv dy, so it really does work. Now you can integrate both sides with respect to y. Normally this is done with respect to x, but again, remember, we've changed the independent variable. So we get y squared v is the integral of y squared dy, and we get y squared v is equal to 1/3 y cubed plus some unknown constant. And then we can finish isolating the v here, and we get v is 1/3 y cubed plus, looks like if we divide by that y squared, oh, my apologies, divide by that y squared, we get 1/3 y plus cy to the minus 2. So there's our v after dividing through by that y squared. All right, we're almost done. Now we just have to undo the substitution and solve one remaining differential equation. So we can now go ahead and take this as dy dx is 1/3 y plus cy to the minus 2. This is now a first order differential equation. Maybe it isn't immediately clear how we can solve it, but notice there are no x's. So you should be able to solve this using separability, where you can bring this over to the other side. So we get this really ugly expression, 1 over 1/3 y plus cy to the minus 2 dy dx is equal to 1. We'll probably take this on to the next page because it's going to take a little bit of work to actually integrate that. So let's give ourselves one more sort of page here. There we go. And I don't think we need that. Okay. Since this is separable, I mean, we've already separated, there is no function of x. There won't be a function of x when you're doing this because, remember, that's the whole point. That's why we did this approach. So we can go ahead and integrate both sides. So we have the integral 1 over 1/3 y plus cy to the minus 2 dy is equal to the integral of 1 dx. All right, at this point, we got to somehow figure out how to sort of integrate this. So I guess we can try multiplying the top and bottom of this expression by y squared. So we can get y squared over 1/3 y cubed plus c dy. And I guess on this side we get x plus another unknown constant, so we'll call that d. Over here, that looks pretty nasty until we recognize that the derivative of 1/3 y cubed plus c, even though that's a plus c and we don't know what it is, the derivative of a constant is 0, and that's exactly what we have in the numerator. So we can do a u substitution, 1/3 y plus c. The du is exactly what we have up there, y squared dy. So we can go ahead and pop that in. Looks like we're going to get 1 over u du is equal to x plus d. Then we can go ahead and integrate that. That's going to be ln absolute value u is equal to x plus d. Throw that stuff in. Ln absolute value 1/3 y cubed plus c is equal to x plus d. I suppose if we want to, we can unpack the ln and get 1/3 y cubed plus c is going to be, well, we would get e to the xd, which we know that that d can sort of slide down in front as a multiplication. So we get de to the x. And I suppose then we can say 1/3 y is de to the x minus that other unknown constant. Multiply by 3, which isn't going to do anything, so de to the x minus c. And then take the cube root if we really want to go all the way explicit, which of course is not necessary, but just for fun, de to the x minus c to the 1/3. There we go. We are basically done. Only thing we need to do is sort of go back and consider over here where we said v not equal to 0. So let's grab that real quick and say what happens if v is 0. Well, if v is 0, we need to think about what v actually means. That's dy dx, so dy dx equals 0. Well, we know that that just means y equals a constant. Are y equals a constant solutions? Well, if y is equals a constant, it's first derivative, second derivative, every derivative is 0. So everything is going to be 0 in here, 0, 0, and 0. So these do work. Are these already included in the solutions that we found? Well, if we go back here and we have this format, notice if I choose d equals 0, then this all just drops out, and I get minus c to the 1/3. But of course, c is just a constant, and raising it to the 1/3 is going to be at a constant. So actually, this is our general solution here. This is our general solution. That's because things of the form y equals k are included. And again, I'm just using a different constant so you guys don't think y equals c means the same constant. So those things that we would have had from our check actually are included here. if you choose D to be equal to 0 and C, well, to be any number so that you get those constants. So there we go. We've solved a handful of sort of higher order differential equations. I hope that while, these sort of are interesting and they sort of rely on these clever substitutions, I hope this also convinces you, though, that this is not a sort of long-term sort of viable method. Any differential, even second order differential equation that involves y double prime, y prime, y, and x, in other words, if nothing is missing, then we don't have a good technique for doing it yet. So we're going to be transitioning now, taking some time to work our way through linear algebra to develop some results, mostly sort of to help us understand what the solution sets to differential equations should look like, so that when we return to higher order differential equations, we know more about what we're really trying to solve. So this wraps up chapter 1 for you guys, which is all about first order differential equations with just a few extra things mixed in. Next, we'll be moving into chapter 2, which will be a complete change of gears, and we'll begin to talk a little bit about linear algebra.